Okay, we want to look at the standard tangent graph and try to understand its behavior so we can graph transformed tangent functions. So we're going to look at y equals tangent of x, just our standard sort of tangent function, and we'll use our unit circle over here to understand its behavior, and then we can graph it in the xy coordinate plane over here. Okay, so over here this is x, of course, and this is y, and over here this is the unit circle. Alright, so if I want to understand the tangent function behavior, I need to first realize that tangent of the angle x is simply calculated as the opposite side of the reference triangle divided by the adjacent side of the reference triangle. So if I start to look at plugging in values of x to this function, those will be angles on my unit circle. So over here, x will be the same thing as the angle that we're looking at on our unit circle. Okay, so that's kind of the setup here, and now we need to start rotating through some angles. So we might start at an angle of 0, or an x value of 0. Whenever x is 0 in this function, in our unit circle, the angle is 0. So whenever our angle is 0, tangent equals 0, right? Because the opposite side, which is in a reference triangle, that's always the vertical side, and the adjacent side is always the horizontal side. Here the vertical side is 0, so 0 divided by the horizontal side, which is 1, gives me a ratio of 0. So tangent is 0 there. So whenever x is 0 in the unit circle, whenever our angle is 0, the tangent of that angle, or y, is also 0. So we get the ordered pair. We could set it up like this if we wanted to. 0, 0. Okay, let's go up here to pi over 2. That's whenever x is pi over 2. Whenever x is pi over 2, y for this function is the tangent of pi over 2. The vertical divided by the horizontal. So in this case, the vertical is 1 and the horizontal is 0. So we get a tangent value here, tangent equals 1 over 0, which is undefined. Okay, so this function is a bit unusual. It's undefined at the angle pi over 2. So let's come over here to our coordinate plane and set up our x-axis. Let's say I want to end at 2 pi. Let's call that 2 pi. Let's be a bit smarter about that. Let's call this 2 pi. If that's 2 pi and I cut it in half, then I'll get pi. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tick marks to get 2 pi. So 5 tick marks will give me pi. And then halfway there will give me the pi over 2 and the 3 pi over 2. Okay? Alright, so the tangent of pi over 2 is undefined. So we can't plot anything on our graph there, but we could sort of indicate that as commonly done, sort of marking pi over 2 as territory that we can't touch. So I'll do that with this dashed line. Okay, now what I want to do is observe the behavior whenever our angle is between 0 and pi over 2. So let's look at an angle that's really close to 0. Whenever our angle is close to 0, the vertical side is small and the horizontal side, oops, sorry about that, the horizontal side is some number close to 1. So we still have a tangent value close to 0 at that point, but it's getting bigger. Okay, so we're starting to come up off of 0 as my angle is getting closer to pi over 2, as I'm moving towards pi over 2. Alright, and if I keep going, let's go halfway between 0 and pi over 2, namely at pi over 4, you can start to see that, hey, my horizontal side is catching up to my vertical side, or my vertical side is catching up to my horizontal side. In fact, they're equal at pi over 4. So if I divide them, my ratio equals 1. So whenever I come over here and my angle is pi over 4, I get this exact ratio, a tangent value of 1. Okay, great. Now let's keep going over here. If I get an angle, I'm moving close to pi over 2. My reference triangle is a bit hard to draw. Not too bad though. Now we can see that the vertical side is getting close to 1 and my horizontal side is getting very small. So I've got a number close to 1 divided by a very small positive number. That's going to give me a really big positive number. So how does that translate to the graph over here? It translates to, as my angle gets close to pi over 2, my y value, or my tangent value, is getting very big. So that translates to, okay, as I'm getting close to pi over 2, I'm going up really fast, really high, and in fact there's no limit on how big it gets, right? Because I can keep getting closer to pi over 2 here, and my horizontal side keeps getting really, really small, very close to 0. So this part of my graph actually approaches infinity. And now if I just connect the pieces that I have here, I start to see that my graph for tangent looks like this. Between 0 and pi over 2. Okay? Now we can pass pi over 2 and start to do the same analysis. And you can see that, remember in quadrant 2, tangent's negative because your horizontal side is negative and your vertical side is positive, which will give you a negative ratio. So now all of my values in this quadrant will be negative. All the values in the first quadrant, the yellow region over here, were positive. So my ratios are going to repeat, right? Whenever I have an angle close to pi over 2, which on the coordinate plane will be somewhere like right here, I still get a very big ratio, but it's a negative ratio. So now my graph's going to be big negative at close to pi over 2. And I bet you can guess that halfway between pi over 2 and pi, if I look at my reference triangle, my vertical side and my horizontal side are equal. So again, I get a ratio of 1, but it's a negative 1. So I'll mark a negative 1 now, and I'll have this point. And at pi, of course, tangent, again, equals 0, because the vertical side is 0, and the horizontal side is negative 1. So at pi, I'm at 0 again. And so this part of my graph looks like this. It's already starting to repeat its behavior, right? Okay, let's venture into the third quadrant. In the third quadrant, tangent is positive again, because the horizontal and vertical sides are both negative, which gives you a positive ratio. And the values are going to repeat again. So now, at pi, I'm at 0. At 3 pi over 2, I'm undefined again, because my horizontal side is 0. So halfway between, at this angle, halfway between between pi and 3 pi over 2, my ratio is 1 again, and it's positive now. So I'm back, let's see, so I'm back up here again. And at, sorry, I'm in the wrong part of my graph here. Halfway between pi and 3 pi over 2 will put me at 1, so I'm up here again. And I bet you can see that this graph is going to do this sort of thing. Okay? And now if you understand that, if you can see that we've already started repeating a behavior, right? This graph has already completed a complete cycle, because now it's already repeating its behavior exactly. So what we learn from this is I don't need to go any further. I can just repeat the behavior. So if I wanted to graph this next part, let's see how I can do this effectively. This part repeated right here. So now I need to repeat this part down here, which will give me this kind of thing. And now I could go on forever to the left and to the right. So what we realize from this is that for tangent, the angle only has to rotate through pi radians for one complete cycle. Okay? That's very interesting. So the reason is because the reference triangles over in the first quadrant here have the same exact ratios as the reference triangles in the third quadrant. So the third quadrant starts to repeat the values from the first quadrant. So we only have to consider from 0 to pi. So typically maybe you would consider 0 to pi, one complete cycle. And that's what you need to know about tangent. Tangent at 0, when your angle is 0, where it starts, it's 0. And then it approaches infinity when you get close to pi over 2. And then at pi over 2 on the right hand side it's at negative infinity, and then goes back up to pi where it's 0 again. And now you have a complete cycle of the tangent function.